Hello, everybody, and welcome to the Northwest Pinball and Arcade Show. We are happy to have you here and excited to have you here at the Geek Gamer TV stage. And starting off today will be Richard Godwin. Please give him a warm welcome.
Hey, I'm Richard Godwin, better known around here as Oz. I'm one of the medics, do a lot of game repair stuff. I have the kids zone. And my day job really is all game repair. I do a lot of it all over, primarily Kitsap Peninsula, but I run south, Tacoma, Olympia, places like that. So today we're going to go over some basic introduction of how to test for power, how to make sure your game's got good power to begin with, and what parts might have failed if your power is not consistent, isn't accurate. We had an issue just yesterday where some of our power supply to our games was wrong. We had 5 pinball machines, 3 sparked up elaborately, and the other 2 melted down because someone accidentally supplied us with 220 instead of 110. We could have avoided all that damage had we tested our power like we should be doing. So it's a good idea to pay attention and move through. All right. So the first thing I want to start with is alternating current. The reason I'm starting there is this is what you're getting out of the wall, sometimes referred to as mains power. This is what the cities and the counties and everywhere are sending us. It should be nominally 120 volts. Depending on where you are, it can drop as low as 110. This voltage, they supply it to us this way because it's easy to transmit. We can easily shift it, send it over long distances with minimal loss of power. In addition, when it gets to your home or to your equipment at home, it's very easy to convert it to a voltage level that you can use, that you need to use. So that's it's pretty basic. The first few slides are going to be simple stuff like that. Transformers. So this is the piece that we use to change that voltage. So it's there. It says change amplitude of an AC signal. Amplitude we tend to refer to as voltage. So this transformer is just a series of wires coiled up together, and that 120 volts gets transferred through basically magnetism. The flowing current creates a magnetic field, and that magnetic field can be picked up and converted again back to electrical current across the secondary coils. This can transfer straight across 120 volts to 120 volts, or more commonly, we use it to step down 120 volts to 6 volts for lights and around 50 volts for coils. Here is a portion of the schematic drawing for Queen Bowler. This is a bowling machine I have built back in the 50s. And if you look in that upper right-hand corner, you can see the schematic diagram for how the coil works. So the long coil that has the loops in it across the bottom is the mains power coming in, again, typically at 120 volts. And then you have the 2 smaller sects up top. The one on the left is 6 volts. The one on the right is 24 volts. So this game uses 6 volts for lights, again, and 24 volts to drive coils. Again, this was built in the 50s, but this is pretty much the standard today. The same system works. So if you look at the left-hand side, you've got the 115-volt 60-cycle plug there. That's what plugs into the wall, goes through that 10-amp fuse. If something's wrong beyond the fuse, if something's wrong internal to the game, it will burn that fuse. If something is wrong prior to that fuse, hopefully it'll blow the breaker at your house. If not, well, you're going to have bigger problems. And then from there, it goes up to the coils. The voltage control plug there, that was something fancy they did in this game. As opposed to most modern, most modern games require either altering lines across the transformer or re-plugging connectors. So, all right. This is a Grand Prix schematic. You can see it's kind of the same way. All the different companies drew their schematics up a little differently, but they all have similar components. So in the center top, you have the plug. It goes down to that yellow and black wires across the fuse, then lighting up the transformer itself, and then transferring down to the 6 volt or 24 volt again coils. This has a third leg from the 24 volt for some higher voltage coils. I don't see it labeled there, but I'm pretty sure it's 48 volts for the entire leg. All right, so that's the AC. That comes in. AC is great, and it works fine for electromechanical machines. But your solid-state machines, anything with a circuit board driving it, the AC is confusing to a circuit board because the power is cycling up and down. So we shift it to a direct current. And that's primary, the direct current, that's what works well for your logic, for your circuit boards to function. And it's also much easier to test and verify that you have a correct voltage. Alternating current, depending on the load, can be supplying a correct voltage, but look like it's supplying too much. All right. So how we convert AC to DC, this gets into the beginning of the circuits and what kind of things we're going to talk about testing later. So linear rectifying, this is the old way of doing it. It required bridge rectifier and a few capacitors, and often this required significant step-up and step-down transformers. So it used a lot of large, heavy equipment. So the linear rectifiers, again, I'll show you a circuit here on the next page, and we'll go through the different piece parts of a linear rectifying circuit. And then there's the switch mode rectifying. This is our more common, this is what everybody uses now. Almost every manufacturer pinball out there uses Meanwell branded power supplies. They're all the same power supplies, and those are switching power supplies. The switching power supply is lighter weight, uses fewer components, but they're at a tighter tolerance than the things with the old linears. All right. So this is a power driver board schematic. This is out of a WPC. I think this was my No Fear pinball machine manual that I pulled this out of. If you look down to J102, which is the lower left, so J102 is my input power. J102 is coming off a transformer, and let's see, what do I got? 50 volts coming out. So it's going to have roughly 55, sometimes 75 volts coming in, alternating current through 8 and 9 is one side, and 5 and 6 are the other. Goes through a fuse, like almost everything does, and then it hits BR3. So BR stands for bridge rectifier. What a bridge rectifier does is it separates the positive and the negative voltages from the alternating current. So in this case, we tap off of the positive side, so we're only getting positive voltages coming out of that bridge rectifier. It comes across that 100 microfarad 50 volt capacitor that you're seeing there, and that capacitor helps limit the high end as well as the low end. It basically steadies it. So instead of having voltage coming out anywhere from 1 volt to 50 volts, it steadies it off, in the case of this circuit, at 50 volts. Again, through a fuse and then up through the coils. So this is a high power coil. So this would be what would drive, power like this would drive your slings and other things on the, other high power coils on the, in the game. All right, so linear power supplies, there's just a little definition of them. So the regulated voltage, you use either a voltage regulator or Zener diodes to lock in that voltage. A Zener diode is a special diode that bleeds off voltage above what it wants to be. So if a Zener is set at 89 volts, everything above 89 volts gets bled off to keep that circuit from from exceeding 89 volts. They usually are adjustable via a pot and are, like it says here, used for logic and voltage-sensitive systems. And then there's the unregulated voltage. This is typically used for things like lights, but they don't care. So if you've got a circuit that's like the 6-volt lighting circuits, the lights will operate at 5 volts. They could run up to 9 volts, and it won't hurt the light bulbs. So this they'll use an unregulated system for that. Also, sometimes an unregulated system is used to feed another system. Very common, again, in WPCs, 90s-era Williams games. There's a 12-volt unregulated voltage that feeds a separate rectifier, a rectifying circuit that smooths it out for individual components, mostly for optos, all the optos, opto isolators, and whatever. All right. Switching power supplies, again, they're self-contained. Switching power supplies are repairable, but they are not built to be repaired. And we'll go over, I'll show, if you guys stay for the soldering that we're going to talk about in next hour, you'll see what I mean. I have some circuit boards that are just not meant to be repaired. They're thin, they're small, they have small lands. They're designed to be mass-produced and thrown away. A lot of these switching power supplies are designed the same way. And another thing about the switching power supplies, the last line there, they must always have a load. If you're running a switching power supply with no load, it can run away voltage and damage the internals of the switching power supply. All right, let's move on to something fun. Testing tools. So right here I have a picture of two different multimeters. I have them up here at the table. This Fluke 289 and then this, I don't even know what it is. Some little yellow thing. So the Fluke 289, that's a high-end meter. Costs a few thousand or a few $100s to buy one of these meters, and you can send them into Fluke and keep them calibrated. They're great, but they're kind of overkill for what we're doing. They're also super sensitive and can be confusing if you're new to using them because they'll jump around. You'll have a good signal, but the Fluke will jump around because the Fluke is auto-ranging. And by that, what I mean is if you look, so currently the Fluke is pointed at the LOZ, basically a low voltage rating. The line above that is voltage, and it's a alternating current, an AC voltage. If I put it into an AC voltage and go to test something with this meter, it's going to start at a 1,000-volt range and then work its way down. So it's a little slower to get where you're going if you know you're looking for 5 volts. Where the smaller, the cheaper meter, these are, I don't know, I think I bought these for like $30 or something. I used to tell people to buy them at Sears, but that's a little gone now. So yeah, but you can find stuff like this online. Even Harbor Freight, if you're not buying their $10 meter, work like these. These you have to set the range. So, all right, we're going to go over a couple different components. First component I want to talk about is a resistor. So because of the fact that the Fluke meter is super sensitive, I couldn't get good pictures for what it was testing because it jumped around. So I have the cheaper meter here set up. So the first, the left-hand picture of these two just shows a 1 and nothing else there. That's indicating that. So so I have this set to voltage. To resistance. I'm sorry, and it's set to the 200 ohm range. This first picture is indicating it's outside of that range. That this resistor is more than 200 ohms of resistance. So the second picture, I've jumped it to the 2,000 ohm range, and now you see the 0.462. But that's 0.462 on a 2,000 scale, so that's really 462 ohms of resistance across that resistor. All right? So the next resistor I have is, it's physically larger resistor, but it actually a lower resistance rate. So at the 200 range, this one came up with 81.1 ohms of resistance. So, and I'm getting somewhere with this. Next page. All right. So this is what I was getting at with this. So I want to show, this is why we have to take resistors out of circuit. So this first picture at 0.543 has got those resistors in series. In series means that they are one after the other in circuit. I just used another jumper to jumper across the two of them. And you see that 462 plus the 81 came up with that 543. The second picture is resistors in parallel. This is what will screw you up if you're testing resistors and you don't remove one leg, if you don't pull it out of the circuit. Those resistors, if you test across either one of them, will come up with 69.2 ohms, which is lower and out of range for both resistors. So this is something you got to be careful of when you're testing these kinds of resistors, resistors in general, when you're testing anything in circuit. So any questions, any comments yet? Nope. All right. All right, next I'm going to move on to capacitors. Capacitors are very common in all of our systems as well. They are a high failure item at this point. Most capacitors were designed to last 5 to 8 years, And most of these games are significantly older than that. Capacitors, however, do not test well with the multimeter. So the only couple of things you can really see with the multimeter with a capacitor is it shorted or open? So a short means the two legs are connected. There's no resistance between them. That's a short. And an open is the other way around. It's there's no connection between the two. Typically with a capacitor, if you hook up a meter and it starts to climb, like the scale starts to climb up and then it reaches a point and it starts to decline, usually that's a good capacitor. But it's, again, not the most accurate test, and I didn't want to get too in-depth into other types of test equipment right now. All right, next we're going to move to the diodes. So this also covers the bridge rectifiers I mentioned earlier. Bridge rectifier is just a series of 4 diodes connected together. The diodes, as you can see in those 2 pictures, I've swapped the leads. So a diode should read as an open if you are going from the positive side across the band to the negative lead. I don't know how well it can. I don't know that you guys can see it all that well with the lighting, but there's an anode and a cathode. There's 2 sides to a capacitor, and these lines are. This is what I was trying to. It looks okay. This is what I was trying to depict in here. So, I'm sorry, I said a capacitor. I meant a diode. So this diodes you don't normally have to pull out of circuit. You can normally test them in circuit. And this is the kind of drop you're expecting. So in the diode check, your meter is actually sending a small amount of current through at a lower voltage rating, and it's reading what it gets back, how much is dropped away from what it had. And so that's where you have the 1 on the one side, which is out of range, open, nothing is there, and the second is 626 millivolts. That's what it received back, and that's typically good. 450 to 700 millivolts is good for most diodes. All right, Darlingtons. So these are common again, 80s through the 90s, even into some of the early 2000s Sterns, these Darlington transistors. This is your tip 102, tip 120. These are what drive your solenoids. So the Darlington transistors that drive your solenoids, the center leg is the ground. The center leg is also connected to the little top hat, the metal piece up top. So what I'm showing you here is ground connected to the top. To each leg, you can see falls on the high end of the transistor ranges. So these are just a couple of internal transistors in the Darlington a couple of different diodes internal to the Darlington transistors. So, all right. Now I'm going to go to the coils. Coil testing is, again, pretty straightforward, pretty simple. You put it into resistance check. Very few coils are going to require you to be above your lowest scale. If they are typically super small coils, like in old EMs, hold coils and things like that. And then you're testing from leg to leg across the coil. You should see usually 12 ohm or less of resistance across that coil. And if you are seeing more than that, like if it's an open, then you've gone too far. Or if it's a short, if the resistance across there is nothing, you get 0.1, 0.2, then that is shorted. I'm sorry. If it's 0.1 or 0.2, the coil is shorted. Anything in excess of what you should expect, no more than 10 to 15 ohms, is most likely an open coil. And it's been damaged in some way. All right, so I'm more of a hands-on guy than just talking about stuff. I don't like just chattering up here. So I'm going to go to this final slide here, which is nothing. And then I want to invite some people up to show you how to use these tools, these multimeters, and show you the difference in how they react to the different, the different components. So anybody want to come up here? Okay, so they asked me to have questions asked at the mic because they're streaming. So if you, that's all right. I'll just repeat his question. So he asked, what is a Darlington transistor used for? In the case of pinball and some of the video games, these Darlington transistors are used primarily to drive either solenoids or flashers. What they do is they allow a 5-volt logic signal to turn on or off a higher voltage signal. So the 5-volt signal comes in, and then they will turn on, in this case, really short, a 25-volt system or 50-volt in order to cause a solenoid to operate. So, all right. So I have this bridge rectifier up here that I think I wanted to show to use first to demonstrate how these different meters look in test, as well as just to see what we're expecting to see. So would anybody like to come up here and use this? Sure, absolutely. All right. You're good right here. All right, so like I said, I have these 2 different meters. We're going to be testing diodes. So testing diodes, I go to the diode check section here. So that one sets on. This is a little more elaborate. It's got a little internal computer.
The diode symbol, right?
Yes, this symbol for the diode, you've got a triangle pointing against a bar, against a line. So the one big positive about the Flukes is super long test leads. They're super long test leads. They're also rated usually for like 1,000 volts, where the cheap meters test leads are normally rated no more than 250. Take the leads. Okay, so taking the leads, go across any 2 legs next to each other. Doesn't matter what color. So currently he's gone across 2 of the legs on the AC transformer, and you see it's jumping, or at the bridge rectifier, and it's jumping all over the place. You see what I was saying? Now swap to this one. So this is why I like the cheaper meters. Honestly, I use them a lot more. So across the same set of legs, he's getting a proper indication of 556. Can you swap your leads over? And now you've got the open. So what we know is we've got a diode across here, and the arrow that was across the diode, I don't remember which way you had the leads, was pointing in one direction and working properly. Yeah, so your arrow is pointing. This.
Black to red, slow.
Well, by design it goes the other. So you can go ahead and hit the next 2 leads, 2 legs, and similar readings, right? Because the diodes are all going to point around together. So go ahead and go back to the other lead. Go back to the other leads, and we'll again see it. It's going to just be a messy answer. So this is jumping around, and it is kind of jumping around at a similar 600, 700 microfarad, but it's also dipping off. So these are the 2 meters, and these are how they compare on indications. Give me just a second. I have other test equipment as well. Sorry, guys. It's been a long weekend already for me, and I'm tired. All right, so we're going to move on to diodes. I'm using these. These diodes are power diodes. These are you're not going to commonly see huge diodes like this being used in any of the pinball arcade games. These are more commonly used in yard equipment. So go ahead and do the same. It doesn't matter. So that's a good question. He asked, did it matter? It does matter. You should check a diode each direction. That way you know that it is stopping the current flow the direction it's supposed to and only allowing as much to pass as it's supposed to the other direction. So again, on the fluke meter, it's jumping all over the place. but we're hovering about 350. Yeah. And then swapping the leads around it's bouncing to open and then to almost nothing because it's blocking. Nice cheap meter. All right. So with the cheap meter, yeah, there you go. So we have to, you've got the blocking. So let's swap around. And bam, there's your up to your 570 again. So the testing these different pieces of equipment, the next thing I'm going to move to is actually a power supply board. And we're going to look at testing on an actual board. So let me grab that off the back table here. So does anyone recognize this board? What game did this come out of? Something Midway. How about something Williams?
Pinball or is it arcade?
This is a pinball board. This came out of a pinball machine. Exactly which machine I couldn't tell you, but this is an System 3 through System 7. System 3 through System 6. Williams 80s era pinball machine. So this takes input from a transformer and steps it up to rectifies it in some places and steps it up to other voltages. So the Williams era machines, Williams machines of this era, the display operates on plus and minus 90 volts. So this rectifies that and creates that 90 volts, as well as shunts the 6 volts across and the higher voltages, the 48 volts for things, and creates a 5 volt also. This piece up here, this component in the very top. So you got this big black frame. I got it. Oh, thanks. Yeah, so we got this big black frame. This is a heat sink because this little silver chip in here creates a ton of heat. Without the heat sink, it'll burn itself up. The heat sinks typically are used as part of the linear voltage rectifying circuit. So let's go ahead and let's talk about testing fuses. Fuses should always be removed prior to test. You're going to test them using the same diode setting, and it doesn't matter which direction you go, but let's see what you got. So testing across that fuse, he's getting inconsistent. Yeah. So, yeah, that was good. Go ahead. Put it back on. So fuses don't need to be tested both directions. A fuse is basically just a wire that is designed to be thin enough to burn up if there's too much current that flows through it. So as long as you have a good signal, then you're good. So testing a fuse, hit it one more. No, just go ahead and hold it. So I don't know if you can hear this at all. Yeah, I don't know if you can hear it. Doesn't matter. So most meters have an audio output that you can hear, a buzz that'll tell you your fuse is good. If you, as long as it's buzzing out or on your meter, it dips back down to near zero, usually 0.1, 0.2 volts, then it's good. So we're at, it's an old fuse. So that's fuses. Again, if you leave a fuse in place to test it, sometimes you'll get bad readings because other components will complete the circuit, especially solenoid circuits, because you're testing right through your solenoids, which are already closed. I don't know. What time is it? 4 o'clock. So let's see. I don't know. There's no other good components on this board to test, I don't think. The voltage regulator. Yeah, so let's talk about the voltage regulator. So the voltage regulator, again, is a silver transistor up top. So these transistors have a relatively high resistance to, when you test them, you test them okay. So diode test, you're in the diode test. you would put the red lead on the housing of the transistor itself. And then usually the first one you do is red lead to ground. So these, I'll take this one. Yep. So these boards usually have a ground path across the outside. You hold it on and steady, and it jumped up to 1400, and then it went into an overload condition. It went too high. Well, I don't know what's causing. Yeah. Well, what's causing that short? Am I causing that short? That's what I'm wondering. Yeah, so be careful of what all you're touching too. So, so that is how you test those pieces, and they're functional. Yeah. So he was pointing at the horrible solder joint on the back, but honestly, I think that's a factory solder position. Yeah, that's where they soldered the screw in. So, all right. Okay. So the question he asked is, could you also test it from the back? Yes. So there's two legs on the back side. You can test across those two legs. Go ahead. So, yep. So testing across those two legs, though, he's getting basically 600 millivolts, again, a diode. Swap them. And on this side, it's open, again, basically just a diode check. Also, if you're looking at the back and you want to do the same test we did, typically the screws are hard to the casing. So go screw to ground plane. And then we get our what looks like a short. Go screw to leg. Either press. Screw, yep. Are you on it? Yeah. So there's our 870, and go to the other one. And 650, 750. Yeah, so these tests, those are tests for, again, for these voltage regulators. So, I don't know. Do I have any questions? I think that's about the extent of what I have prepared, but there's often a lot of questions about different things. So, are you on? That sounds on. Yeah.
Hello?
What can I say?
Oh. Can you hear me? Okay, yeah. Can you talk about some of the dangerous things you've seen out there, or you've been shocked, or
Oh, yeah.
yeah, or what precautions you would do if you're trying to get started in this?
Okay.
And are old ones worse than new ones, or for getting shocked or killed?
Okay. So, things I've seen. All right. I have been shocked many, many times. One of the primary culprits of getting shocked is poor grounding. So all these games were designed with different grounding paths to make it safe for you to touch to operate the games. If those grounding paths are broken in any way, then you can become the ground path. So some of the ways I've been shocked commonly, pinball machines, if the ground plug, if the ground pin on the plug has been broken off, they will have what they call a floating ground. Basically, they are ungrounded, and you can get shocked touching them. Although it's more common for you to get shocked if you're touching one pinball machine and the one next to it that actually is grounded. A shorter, easier path to ground, and that's when you'll get shocked. And that's not bad. Usually, doesn't usually hurt. Just tingles. Just enough to let you know that something's wrong. So that's one area I've been shocked fairly commonly. Let's see, other shocking issues. Capacitance. So I mentioned the capacitors earlier. Capacitors will hold a charge, and sometimes they hold a charge over an extended period of time. And some components back in the era of vacuum tubes hold charge much longer than other things. A vacuum is very good at insulating. Primary vacuum tubes you see nowadays are the CRTs, the cathode ray tubes in the arcade games. Those can hold a significant charge voltage-wise. I've been hit by 6,000 volts out of one of those because it wasn't grounded off properly. So you got to be careful around the anode cup area. I don't have a monitor right here, but there's this big fat red wire on the backside that plugs into the top of the back of the CRTs. That's a very dangerous wire to touch. In operation, that runs 18 to 25,000 volts, and even when it's turned off, it can retain significant voltage. Large capacitors on circuit boards. There's not really something super large here, but let's just pretend this thing is bigger. You get these capacitors on circuit boards that are very large and also retain a large charge. And I have taken boards out of games and sat them in my lap and burned a hole in my pants. So you got to be careful with these. If there's 2 pins on the bottom, and if those 2 pins are, if the easiest path between those 2 pins is your leg, that's what it's going to take. I don't know off the top of my head what else I've been shocked that you guys might run into. I mean, I was carrying a monitor once, and somebody plugged it in, and that shocked the shit out of me. So, yeah, that was great. So, luckily, there was one person in the room who understood what was going on, and he unplugged it, because I couldn't. At that point, my arms had locked up, and I couldn't let it go. And so this is something to think about with current and voltage. Depending on where it enters and exits your body, it can lock muscles into place, and you can't control them. Your arm just locks into place, or your leg locks into place until the voltage goes away. If you are working on something like that, you have to cut that voltage. It's the only way to remove yourself. I mean, I've heard of people physically yanking themselves off of, like their left arm's locked on, and they use their right arm to knock their left arm off, but you could just end up with both your damn arms locked on. So, it's not a good situation. So definitely shock is a possibility. But I feel like in our games, it's pretty minimal. As long as you are aware and you aren't leaning across different circuits and things. So, any other questions? Anything else? I want to hear about how let's see, that was my worst, the stupid monitor shock. I don't know. Capacitors, monitors. So, we good? Nothing else? All right. I think that's all I have for this. The next seminar that I'm going to do will be soldering. We're going to talk a little bit about safety of soldering, and then I'm going to have some soldering equipment set up here. I'm going to have anybody who wants to come up here and solder some components into place, remove some components, and just get an idea of how of what effort it's going to take to solder things like a solenoid versus on a circuit board, and how delicate circuit boards are and how easy they are to destroy if you aren't careful.